not sure where I left off previously. So, Nick, Brosick, suppose you have a random variable that is normal 0, 1, and you take a random sample of size n, say, and you square them all, and then add them up. What's the distribution of the resulting sum? Chi-square with how many degrees of freedom?
N.
Right, sample random. Suppose that it's not normal 0, 1. Suppose that it is this normal random variable has a mean mu and a variance sigma squared. You collect a random sample of size n, and you don't recenter it and you don't rescale it. You just take a random sample of size n, square each one, and you add them up. The resulting distribution is the sum of the xi squared. So the xi are normal, mu sigma squared distribution. So the xi are distributed as normal, mu sigma squared, and you construct a random variable called z, which is the sum of the xi squared from I equal 1 to n. IID. And Nick just told us that if mu was 0 and sigma squared was 1, it would be chi-squared with n degrees of freedom. So all I did was change things a little bit. I said that the mean of mu and variance is sigma squared. I square them and I add them up. So what do you think the distribution is? This is your question. He just told me that if I had the sum of squared normals, it was chi-squared. It's still chi-squared, but does it differ from the one that Nick got? So, it's still the same number of degrees of freedom, but it's something different. Nick had one where the underlying normal random variable had a mean of 0 and a variance of 1. You got one where the underlying normals have a mean of mu and a variance of sigma squared. And you didn't recenter or rescale. So you were right, you said it's chi-squared. But how does your chi-squared differ from Nick's? Anybody know? That's a non-central chi-square. What is it? How does a chi-square of the same number of degrees of freedom differ central versus non-central? D or die? D? Whoa. No, nobody here. D? Oh, you got to raise your hand about that. I see you. That's my arm. You know what the difference is? Right. We know what a chi-square looks like. We'll start by trying to draw that one. So if we have a chi-square random variable, then its density looks like that. Right? So suppose that the chi-square was 7 degrees of freedom, and the underlying normal from which it was constructed had a mean of 0 and a variance of 1. And now I give you another bucket of normal random variables where the mean is not 0 and the variance is not 1. And I construct a chi-square of that. How would that look relative to this one? Pushed off a little bit. So this might be chi-square with 7 degrees of freedom and some non-centrality parameter that we'll refer to as lambda. And the implication for the tabulated critical values in the chi-square tables is that there's more area in the upper tail. So probably, again, in the beginning statistics class you had, your instructor gave you a homework assignment that said, for a chi-square with 7 degrees of freedom, what critical value cuts off 10% in the upper tail? And you got out your chi-square table and you looked up, I said 7 degrees of freedom? 7 degrees of freedom. You looked up 7 degrees of freedom in the 10% table, and that told you what number on the horizontal axis would cut off 10% in the upper tail. So if you did that, and I don't remember what the critical value is for 10% of 7 degrees of freedom, but whatever it is, we'll call it C star. So for the central chi-square, it puts 10% in the upper tail. For the non-central chi-square, there's more probability in the upper tail. Why is that of interest to us? Well, when we're doing hypothesis testing, sometimes we use a chi-square statistic. And the chi-square statistic that we use is predicated on the hypothesis null being true. Remember I said that we specify our null hypothesis to be something that we believe to be true but hope isn't? So when we're using a chi-square statistic to do a test of hypothesis, and we're going to do some of that later, that's other events, then the test statistic is a central chi-square under the null. But suppose that the null is wrong. Oh, and remember, this type 1 and type 2 error business. We choose the level of the test so that we reject a true null only 10% of the time. We would hope that when the null hypothesis is not correct, that we reject it with a higher well. Under the null hypothesis, our test statistic is a central chi-square. But under the alternate hypothesis, what distribution do you think it has? Non-central chi-square. Fortunately for us, because when it's non-central chi-square, the probability of seeing an extreme test statistic is much higher. So we're more likely to reject the false null. So these remarks are all by way of helping you to see why I'm asking these questions and where we're going.
Can you explain this?
Oh, This is a picture that he found on my website. And this figure comes from Poirier. Comes from where? It might, but I think I Xeroxed it out of Poirier's. And what it shows is the connection between all the common probability distributions. In the middle is the normal. This little box has Poisson written in it. We're going to talk about Poisson distribution later on. And there's a dashed line which connects the Poisson box to the normal box. And one of the things that we know is that as lambda, the rate parameter in the Poisson distribution, gets large, the Poisson random variable can be approximated by the normal. Over here is the binomial. One of the things we learned in basic statistics was that for large sample sizes, the normal is a pretty good approximation for the binomial. How did Monsieur Poisson derive the Poisson? Well, he started with a binomial. And what he realized was that if we, and the mean of a binomial, by the way, is n times p. And so he was able to derive the Poisson from a random variable that started out as binomial. Okay? So this just shows how all the different probability distributions are related.
So this is of non-central chi-square inject null hypothesis.
Under the null hypothesis, depending on the test, again, in beginning statistics, you use z-scores to test hypotheses about the population mean of a univariate random variable, right?